Okay. Yeah, so I might have to just let me check. Yeah, okay. So uh, okay, so let us just look at this mean term expansion. So last time we said that uh, the mean term expansion of a function is unique. So let us just look at that aspect. So first of all, I mean acceptance by complements. That means I mean this is kind of definition of complement only. So similarly, acceptance of product. So x and y, or you can say the product of x and y is one. So x and y is also is often called a product. So yeah. So x and y is one if and only if both x and y are one. And for acceptance of sum is at least one of u. I mean, either you should be one or he should be one. Of course, both of them can be one, so it's not exclusive. Now, mean term expansion is of course sum of distinct mean terms, and so what's the mean term? A mean term is a product of. So if you have uh, n variables, if your function is defined on n variables, then a mean term is a product with n distinct literals. All right, uh, n distinct literals, or yeah, that is n literals derived from distinct variables. All right, so acceptance of a mean term. So the important thing is that acceptance of a mean term is due to acceptance of exactly one mean term. Okay, exactly one mean term can be true. So, I mean, it's not difficult to see that, but we'll just see how we can just show that. So now, if uh, you consider two distinct mean terms, mi and mj, on the variables, let us say x1 and xk. So these two are distinct. So these must differ in some variables. So you have m1, m1. Sorry. So m1 is different. Is say you have l1, l2, lk. Okay, and m2 you have l2 dash. Just a minute, please. Someone is. All right. So yeah. So sorry. This one will be L1 dash, L2 dash, so on, LK dash. Now, since they differ, so they will differ in at least one variable. So this is for x1, this is x2, this is xp, this is xk. So there must be one position where they differ. All right. So here it is, if it is say LK, then this one must be LK dash. Okay. And of course, to now to make this mean term true, say if M1 is true, then you'll have L1 equal to L2 equal to LK. I mean, also you can put L. Oh, sorry. Okay, LK equal to L LP rather. This one will be LP. This LK is equal to true. So for M2, so M2 you have LP dash, right? You have LP dash. So this one is going to be, this one is 0. So M2 is going to be 0. M2 is going to be 0. So exactly one mean term only can be true at a time. Okay. For any truth assignment. So that is the thing. So this ensures that the mean term expansion is unique. That means for each assignment of truth values, you can have only one mean term true at a time. Okay. So that is one way of showing that the mean term representation is unique. Now, these things we have discussed before. So, number of Boolean functions we have discussed before. You are familiar with this number, 2 to the power 2 to the power k, if it's a function of k variables. Okay, function of all right. So you have so many distinct Boolean functions. We have seen this before, so we'll not dwell on this more. All right, so by mean term expansion, of course, you know that there are 2 to the power k mean terms. And each Boolean function, because only one mean term can be true at a time, so how can you define your Boolean function? You define your Boolean function by choosing a subset of this 2 to the power k mean terms, and you know that there can be a total of so many, distinct subsets. All right. So that also gives you this way also you can say that you can have so many distinct Boolean functions. All right. So I mean that. Okay, we have seen some of these already. Um, Again, the serial parallel switching circuits we have seen at the beginning of the course. So we'll not again go into that. Okay, let us look at Shannon decomposition. Shannon decomposition is, so suppose you have a function of n variables, okay? Now, when you construct the truth table, okay, so this is, you have a function of n variables, so x1, x2, xn, all right, and you are constructing your function. So this is your f, all right, and now you can divide this into two parts, okay. You can divide this into two parts. Here x1 is 0 and here x1 is 1. So if you do it that way, so you can think of this as say a function f1 and this is a function f2. So this is one truth table, okay. There's a smaller truth table. If you just consider these functions, and so this is function is f such that x1 or sorry, this you can think of f1 such that x1 is equal to 0 and f2 you can say is f1. I mean this is with x1 equal to 1. All right. So this is f1 restricted to 0 and this one is f1 restricted to 1. All right. So that is what we are saying here. So you can say that f is equal to x1, or you can say x1 bar times f1 plus x1 times f2. All right. So what you can see is that when this is So F1, this is true when x is 0, right? This is true when x is 0, and then this is false, and this is true when x is 1. All right. So really, this is a kind of, this is a selector. All right, this is a selector. So really, what you're doing is you're doing a selection. If you think in terms of a multiplexer, if you think in terms of a multiplexer, you're, yeah, sorry. Think in terms of a multiplexer. So if you put x on here, so this is 0, this is 1. So you're selecting F1 and you're selecting F2. All right. So this is your function f. This is what you're doing. All right. And what is so this one is really f2, and this one is f1. All right. This is f1 and this is f2. All right. So this is the idea of Shannon decomposition, and this can be carried out recursively. So these are also called Shannon cofactors. Okay, these are also called Shannon cofactors. Okay. All right. So, well, just as you can do it this way, you can also take the dual approach. You can also take the dual approach. So, this is expressed as a sum of products. This you can also express it as a product of sum. The duality is not hard to see. All right. Because when x1 is 1, when x1 is 1, this is true. And this always, this whole thing is true. And so, and here, value, you can say f is determined. This is, as you have seen, this is f2. All right, this is f2. It is determined by f2 when x1 is equal to, sorry, I made a mistake here. This is when x1 is 1, and this is similarly this part is true when x1 is equal to 0, and here f this is of course f1 is equal to 0. All right. So you can express it in both forms. All right. You can express it in both forms. Now, so it is quite evident that you can carry on this process recursively. Okay. Of course, multiplexer decomposition is, multiplexer realization is applicable for this form of Shannon expansion. All right. So you can carry on this process recursively. All right. You can carry on this process recursively to get a multiplexer realization of the function. All right. We have already seen some examples of Shannon decomposition. So if you carry out Shannon decomposition, you can also express the function in so you can express the function in this form. All right. 0, 1. Okay, so x1 is equal to 0, and you can say x1 is equal to 1. So you can just remove it. All right, x1 is equal to 0 and x1. So if you have a function of, let us say three variables, x1, x2, x3. So at this stage also, you can do further, the based on x2 equal to 0, x2 equal to 1, and here again you can do a division, x2 equal to 0, x2 equal to 1, and you can carry out another x3 equal to 0, x3 equal to 1. So this you can carry on, in fact. You can carry on this decomposition. All right, and finally at the leaf nodes, you will have, what will you have at the leaf nodes? Can anyone tell me what values you will have at the leaf nodes? Yeah,
0, 0, f0, 0, 1.
You'll have the constant value, 0, 1, whatever. So you'll have those values. Now note that some of the sub functions may be identical. I mean, let us just say, take this. Let us take an example. So suppose this is also, so here this sub function is identical, as you can see. This is the same as this really. All right. Um, and we can just say that now these two are not identical, but these are complementary. All right, these are complementary. So you can have some reduction. So you could say that uh, instead of writing this way, x2 equal to 1, you could write it this way. All right. So similarly, for complementary functions also you can have this kind of reduction. So this can give you, I mean, you're expressing the function f is expressed as a decision diagram. In fact, it can, because the decisions are binary, it's also called a binary decision diagram. Now, BDD has many interesting properties. It can be shown that, so variables, you have something called also called ROBDD. All right, so here basically you have order on the variables. If you look at this original diagram, note that after you have say decided on x1, it is not really essential that this you have to decide on x2 now. You could have decided on x3 also at this in this branch. You could have considered x3 equal to 0, x3 equal to 1. It is possible. Okay, you could have done that, but in that case, so if the decision variables follow an ordering. So here, of course, there is a simple ordering. The ordering is x1, x2, x3. So it can be any permutation of this, even if you choose ordering. And if you don't choose ordering, of course, the left and right branches could be evaluated independently. But in particular, if you have this, so you understand what ordering is, and the other part is reduction. So reduction meaning that you are factorizing out the common parts or complementary parts. So this reduction can also be shown to be a unique representation. Now, if you compare, so compared to the mean term representation is also called DNF representation. Representation can be much smaller or compact. All right. So this is just for your information. So, uh, uh, but there is a catch here. This is for suitable ordering. And as you can see, uh, n factorial possible orderings. Of the variables. Now, there are heuristics which can help you to get a good ordering, but it doesn't guarantee that you can have the best ordering. All right. Uh, just a minute. I'll just be back in a few. All right. So this is just a very quick introduction to binary decision diagrams. So these binary decision diagrams are also follow from the Shannon expansion or Shannon decomposition of a Boolean function. Okay. Now we will take a look at another aspect which is called functional completeness. So we have seen that in some cases certain subsets of functions are functionally complete, but we noted that it is I mean, if you are given a set of functions which are not functionally complete, then it's not so easy to show that those are not functionally complete. So let us just let us consider. So Emil Post is he was a mathematician who studied functional completeness. So let us just see. Let us just look at his treatment. So he considers 5 classes of Boolean functions. These are 5 classes of Boolean functions. So one class is called the truth preserving or T preserving Boolean function. So T preserving Boolean function must satisfy this requirement. That is, if all the variables are true, then the value of the function must be true. Irrespective of the values, irrespective of the value of the function for other combinations of the variables, other truth assignment of the variables. So when all the variables are assigned true, then the value of the function must be true. That's called a t-preserving or truth-preserving function. Similarly, you have f-preserving. That means if all the variables are assigned the value f, or if all the variables are false, then the value of the function must be false. So that is called a f-preserving function. I mean, again, as you can see, it's a class of function. A function is f-preserving if this property is satisfied. Now, there are some functions called counting functions. So counting functions, so to understand counting functions, we have to understand the concept of dummy variables. Okay. So in fact, when you consider, when you consider this Shannon decomposition, oh sorry, not here, okay. So sometime back so you expressed f is equal to x1 f1 plus. So what is this f1? So this f, it's say it is defined on x1, x2, xk, all right. And what about f1 and f2? So these are basically defined on x2, all right. Now we could also say actually we these are defined, but we could also say that f1, f2 are defined on, let us say, x1 and x2, where x1 is a dummy variable. What it means is that, okay, so this one is, what it means is that this dummy variable, what it means is that f1, f2 do not depend on the truth assignment of x1. All right. That is, so in other words, f1, let us say f1, 0, if we say literal L2 dot dot LK is equal to f of 1 L2 so this is the formalization of the idea of a dummy variable. All right. So you understand what a dummy variable is, right? So this is the concept of a dummy variable. So that is the thing. F is invariant to changes in a dummy position. But what is this counting? So let us come back to counting. So if you ignore the dummy variables, so if you just ignore the dummy variables, that is position I isn't dummy. So if position I isn't dummy, then a change in the value of a non-dummy variable will change the value of the function. All right. So if uh, sorry, this one should be if position P isn't dummy. Position I, this is okay. Position, the definition for position I is fine. Position P should not be a dummy variable. So if you make a change, if you make a change in the value of a non-dummy variable, okay, if you make a change in the value of a non-dummy variable, then the value of the function will also change. Okay, that is, so that means uh, if you change the value of a non-dummy variable, the value of the function changes. So in that sense, it's a counting function. Okay, it's a counting function. So each distinct, so any change in the position of a non-dummy uh, variable leads to a change in the value of the function. That is the idea of a counting function. All right. Then you have the concept of a monotonic function. So concept of a monotonic function is of course straightforward. You're already familiar with the idea of a monotonic function. So here, if we consider the following order, that is, if we consider this order, so of course, actually, uh, 0, of course, is strictly less than 1. 0 is strictly less than 1. But if we consider two variables satisfying this, okay, x less than or equal to y. So if you have x, y, so what are the combinations which satisfy this? So if x is 0, y can be 0 or y can be 1. And if x is 1, then y can only be 1. So these are the three values which satisfy x less than or equal to y. Okay. So a monotonic function has this requirement that if x is less than or equal to y, then fx must be less than or equal to fy. Okay, that is the usual definition of uh, monotonicity. And then you have another class of functions which are called self-dual functions. So self-dual functions satisfy this property, that is, if you complement all the values of all the variables, then the value of the function also gets complemented. All right. So these are this is the definition of self-dual This is the definition of a self-dual function. So now we just come to the statement. So a set F of Boolean connectives, or if a Boolean functions, is functionally complete if and only if for each of the 5 defined classes there is a member of F which does not belong to that class. Alright. So you must have, so if you have a set of functions, then you must have, the statement of the theorem is that it is functionally complete if and only for each of the 5 defined classes there is a member of F which does not belong to that class. Alright, I think we'll stop here now.
Yeah, I think let us stop.
Yeah, so we can continue in the next class. Okay, thank you.